Hi, my name is Meryem Essaidi, and I'm a PhD student at Princeton University. I'm going to present work on credible strategy-proof, optimal, and bounded expected round single item auctions for all distributions. And this is joint work done with Matheus Ferreira and my advisor, Matt Weinberg. Online auctions play an important part in many internet applications, such as eBay. In particular, the biggest revenue source of many companies like Facebook or Google is from online advertisement. And so reasoning about which auctions are best to use is very relevant. In the early days of online advertisement, first price auctions were very popular. How do first price auctions work? There are bidders, they're going to place bids on a single item, and then the person with the highest bid wins the item and pays their bid. However, people didn't really like the first price auction because it was not strategy proof for bidders. So bidders did not have incentive to bid their true value, and they were being strategic. And because of that, this created instability, which led to inefficiencies and loss of revenue. Because of the limitations of first price auctions and online advertisement, the internet popularized second price auctions. And the way second price auctions work is that bidders are going to place bids on a single item. The person with the highest bid wins the item, but this time they pay the second highest bid. For example, if you look at the example here, if we have two people, Alice and Bob, who are bidding for an item, let's say Alice bids 80 and then Bob bids 20, then Alice has the highest value here. So she wins the item and then she pays the second highest bid, which is 20. However, and second price auctions, unlike first price auctions, are strategy proof for bidders. And so that was a good thing. However, second price auctions are not strategy proof for the seller. So the seller can be an adversary, and then here's an example. The same as before, Alice bids 80, Bob bids 20. There is nothing stopping the seller from telling Alice that the second bid, highest bid is actually 79 and pocketing the 59 difference here. So traditional auctions always assume that the seller was honest, but it turns out that the seller isn't always honest, as we saw in this example here. And so the second price auction is not strategy proof for the seller. In the example that we saw here, the seller has incentive to cheat. And so we ask ourselves the following question, which is, are there revenue optimal auctions that are also credible for the seller and not just the bidders? And we're going to call this property, the fact that an auction is strategy proof for the seller, we're going to call that credibility. So we need to make sure that the auctions that we consider prevent any cheating from both the seller and the bidders. That is, we want the auctions to be credible and truthful. So what does it mean for an auction to be credible? An auction is credible if the seller has the incentive to be honest, even when permitted to cheat in ways that are undetectable to bidders. What does it mean for an auction to be truthful? An auction is truthful if bidders have the incentive to bid their true value. And so we want auctions that are, 1, revenue maximizing, meaning they are optimal. 2, strategy proof for the bidders, meaning they are truthful. And 3, strategy proof for the seller, meaning that they are credible. And this leads us to our motivating question here, which is there a credible, truthful, and optimal auction? Previous work already answered this question, and they showed that the ascendant price auction is the unique auction that is credible, truthful, and optimal. However, the ascendant price auction can require a number of rounds that is unbounded. And here, a number of rounds or communication complexity is defined as the expected maximum number of times that any bidder communicates with the seller. In fact, they proved a whole trilemma, which is the following. 1, the ascendant price auction is the unique, credible, truthful, and optimal auction, but the number of rounds can be unbounded for the ascendant price auction. 2, The second price auction is the unique, truthful, optimal, and one-round auction, but it is not credible. As we saw in the example before, it's not credible, meaning that the seller has incentive to cheat. So the seller can cheat. And three, the first price auction is the unique, credible, optimal, and one-round auction, but it is not truthful, meaning it's not strategy proof for the bidders. So these limitations lead us to a more specific motivating question, which is there a credible, truthful, and optimal auction that has constant rounds? Again, remember we saw that the ascending price auction is the unique auction that is credible, truthful, and optimal, but it can have unbounded rounds. And so now our question is there an auction that is credible, truthful, and optimal, but that has constant rounds? This question was also answered by previous work. Ferreira and Weinberg circumvent this dilemma and introduce a new mechanism, DRA, which stands for the Deferred Revelation Auction. And DRA is credible, truthful, and optimal, and only requires 2 rounds. And they are able to do this by using crypto. So this only holds under the assumption that the auctioneer is computationally bounded and the existence of cryptographically secure commitment schemes. So they're able to get around this impossibility result by using crypto. So they have this new mechanism, DRA, that is credible, truthful, optimal, and only requires 2 rounds. So they introduced this new auction, the Deferred Revelation Auction, and it's a modification of the second price auction. Initially, the auctioneer requests all bidders to cryptographically commit to their bid and submit a deposit. So they encrypt their bid, they send the commitment to the seller, and then they submit a deposit. Later, the seller requests all bidders to reveal their bids. And if a bidder refuses to reveal that bid, then their deposit is forfeit. So they lose their deposit, and that deposit is paid to the winner of the auction. However, this scheme, DRA, doesn't extend to even a single buyer with a valuation drawn from a regular distribution. And so they have this new mechanism, which is credible, truthful, optimal, 2-round, but that doesn't work for all distributions. And this leads us to the main question of our paper, which is there a credible, truthful, and optimal auction that is constant rounds and that works on all distributions? So recall that we saw that the ascending price auction is the unique, credible, truthful, and optimal auction, but it required unbounded rounds. And then we saw that DRA is credible, truthful, and optimal. It only required 2 rounds, but it didn't work for all distributions. So now we want to see if there's a credible, truthful, and optimal auction that has constant rounds and that works for all distributions. And the answer to this question is going to lead us to the main result of our paper, where we are going to introduce a new single item auction that is credible, truthful, optimal, that ends in constant rounds and expectation, and that works for all distributions. So before I introduce ADRA, I'm going to talk about the model first. In the model here, we're going to focus on the setting where we have a single indivisible item for sale. We assume that there are n bidders with private independent values drawn IID from some distribution D. The seller knows D. The bidders have quasi-linear utility, meaning that their utility is just their value minus whatever payments they make. And the question that we're trying to answer here is, again, is there a credible, truthful, and optimal auction that has constant rounds and that works for all distributions? And the answer is yes, we do have a new single item auction that is credible, truthful, and optimal, that has constant rounds, and that works on all distributions. So our work proposes this new auction, ADRA, which stands for the Ascending Deferred Revelation Auction. And it extends the DRA results to all distributions, and it has constant communication complexity, or rounds, in expectation. And the way we get this is by using dynamic deposits. Informally, our main results are under the existence of cryptographic commitments. the main result is that when bidders are drawn IID from some distribution D, there is a credible, truthful, and optimal auction with constant communication complexity. So how did we come up with ADRA? First, I'm gonna go over why ADRA did not work for all distributions, why ADRA was not credible for all distributions. The original problem is hard because of the ability to submit fake bids. The seller can submit fake bids and the bidders can't tell if the bids are fake or not. Recall where the example that we saw where the seller just pretended that there was a second highest bid of 79 when the second highest bid was actually 20. DRA helped with this by introducing deposits that penalize any fake bid submissions. But DRA didn't work for regular distributions because sometimes there is no deposit that is big enough to remove the incentive for the seller to place fake bids. And here's an example of why there might not always be a deposit that is big enough to make the auction credible. If you look at this example here, we have a single bidder that is drawn from the equal revenue distribution. And the equal revenue distribution has this property that whatever price you set, the probability that the value is greater than the price is 1 over the price. And so the expected revenue is always P times 1 over P, which is 1. And here, the seller has this strategy where they can extract revenue that is greater than this one here by doing the following. They submit, if the deposit has value K, they just submit 2 fake bids of value 2K and 4K. And they reveal all bids unless the value of this bidder is between these 2 fake bids. So when V is between 2K and 4K, they conceal this 4K right here and pay the fine of K. And this is going to get them revenue strictly greater than the 1 here, because in the first case, when the value of the single bidder is less than 2 times K, then the seller doesn't get any revenue, so they get revenue 0. In the case where the value is greater than 4K, the seller gets revenue 1 here. They reveal all bids, they don't pay any fines, they get 4K times 1 over 4K, which is 1. And then in the case here where the value is between the 2 fake bids, 2K and 4K, they conceal 4K, so they lose a K here. They pay this fine of K, but they get revenue 2K. And so this gets them a strictly positive extra amount compared to if they had executed the auction honestly. And so this is not credible. So DRA is not always credible. So when the distribution was bounded, reasoning about the size of the deposit was easier. You can just set the deposit to be greater than the max value of the distribution. And this removed any incentive for the seller to submit any fake bids, since the seller can never make more than the deposit they lose when they submit a fake bid. For example, if let's say there's a single bidder, a single item, and the value of that single bidder is drawn from uniform 0 to 100, then a deposit of 100 makes the auction credible, because no matter what revenue they can extract, it's never going to be greater than 100. And so if they place a fake bid, they have to pay 100, and so that's not going to be profitable for them. And we want to leverage this for distributions that are not always bounded. And we leverage this property by using dynamic deposits. And the way this works is that in each round, our algorithm ADRA is going to have a deposit that increases to the current round's maximal possible value. So in a way, it's like we take this distribution, we split it into intervals that are bounded. And then in each interval, we set the fine or the deposit to be the maximal value of that round. And now that I've talked about the intuition of ADRA, I'm going to just present ADRA and explain how it works. Initially, any bidder I is going to send a cryptographic commitment CI to a bid BI without revealing any further information about their bid. The auction is then going to proceed in rounds, and in each round, we have as invariant that all bidders that have not yet quit promise that their bid is greater or equal than Q, where Q is the current bid lower bound. And to ensure that no bidder lies by claiming that their bid is higher than Q when in fact it is lower, they are required to deposit a quantity, a deposit, F of Q, that is greater than Q, and that deposit is forfeit if they lie. Here, the F of Q, F can be any increasing function. Then in each round, the auctioneer asks all the remaining bidders if their bid is greater or equal than the next bound, which is F of Q. And a bidder quits if their bid is not greater than F of Q, otherwise they remain in the auction. If two or more bidders raise their bid, the auction proceeds to the next round and asks the bidders to increase their deposit to F of Q, which is the next level. Otherwise, the auction ends and the auctioneer asks all bidders, including the ones that have already quit, to reveal their bid. The auctioneer then forwards these revealed bids to all the other bidders and awards the item to the winner. If, however, some bidder does not reveal their bid or is found to have cheated in the prior round, then they lose that deposit and that deposit goes to the winner. And the winner is going to pay the second highest bid or the max of the second highest bid and the reserves. These deposits that the bidders pay have this positive externality of removing any incentive for the seller to cheat in ways that the bidders cannot detect. And so the seller is going to face a trade-off. They can, on the one hand, they can commit fake bids and selectively reveal them. But on the other hand, for every fake bid that they conceal, they have to pay a deposit. And so this makes ADRA credible. The communication complexity can also be good because the rounds are defined by this function f that can be any increasing function. And so there is a way for us to set this function as, to set this f as a function of the distribution in such a way that makes the number of rounds required constant. So that's the ascending deferred revelation auction, or ADRA. So this is more intuition about how we came to make ADRA. So ADRA is an intermediate mechanism that goes around the limitations of DRA and the ascendant price auction by combining the properties. On the one hand, if you compare ADRA to APA, then you can see that ADRA proceeds in a similar fashion to the ascendant price auction, because in each round, if a bidder is still in the auction and is bidding B, the seller is going to ask that bidder if they wish to increase their bid to F of B, where F is any non-decreasing function. Usually in the ascendant price auction, the increments are additive by epsilon. So the function F of B in the classical ascendant price auction is just F of B equals B plus epsilon. And APA, the ascendant price auction, needs these additive epsilons to be as small as possible so that even though the ascending price auction can have other increasing functions, the APA needs these additive epsilons to be as small as possible for it to maximize revenue, because if you make epsilon bigger, then you risk losing epsilon in revenue. So you need these epsilons to be as small as possible. But in our ADRA, our F of B can be anything. And in particular, we are going to focus on a case where we have multiplicative increments of epsilon. So our F of B can be 1 plus epsilon times B. And that is the difference between APA and ADRA. ADRA is also similar to DRA because just like DRA, all bidders are required to commit to their bid before the auction starts and they submit a deposit. The difference, however, is that in DRA, the deposit is fixed, but in our algorithm ADRA, the deposit increases the longer a bidder stays in the auction. And a significant technical portion of previous work by Ferreira and Weinberg deals with finding sufficiently large deposits to incentivize credibility. But our work is using adaptive deposits that increase the longer a bidder remains in the auction. And so this gives us a mechanism that is credible for a larger class of bidder valuations and that requires only a constant number of rounds in expectation. This is all to say that the important takeaway about the ascending deferred revelation auction, or ADRA, is that it is optimal, meaning that it maximizes revenue. It is truthful, meaning that the bidders bid their true value. It is credible, meaning that the seller has no incentive to cheat. and it has constant communication complexity. And this holds for all distributions. And it has constant communication complexity because we have this function f of b that we can set to be as a function of the distribution and make it so the number of rounds required are constant. So again, ADRA is optimal, truthful, credible, and constant round, and it works in expectation, and it works for all distributions. Finally, another advantage to our algorithm ADRA is that it offers exponential improvements in communication complexity over the classical ascending price auction. Remember, we said that just like APA, the seller asks the bidders to increase their bid to S of B greater than B, where F is some increase in function. For APA, we have to have F of B equals B plus epsilon. So we need these increments, these additive increments of plus epsilon that need to be as small as possible. And this is because we don't want to lose the epsilon revenue, but for ADRA, our F of B can be anything. And here, if we set our F to be this multiplicative increment of epsilon, then we can get exponential improvement in communication complexity. Another advantage of ADRA is that the bounds are scale invariant. And if we let this epsilon right here, if we use this function, these multiplicative epsilon increments of 1 plus epsilon times b, and we let this epsilon right here depend on the distribution d, then we can get constant communication complexity. And we have an exact, we have an expression here for the number of rounds required. So basically, if we, for ADRA, if we use multiplicative increments, for ADRA with reserve R, if we use multiplicative increments of epsilon, then the communication complexity is going to be log base 1 plus epsilon of the revenue of this auction over the reserve. And applying this, a first example here would be if we set epsilon to be applying this, if let's say we have n bidders that are drawn IID from the exponential distribution, then if we set epsilon to be equal to log n, then the number of rounds is constant in expectation. The second example here is if we have n bidders drawn IID from the equal revenue distribution, then if we set epsilon equal to n, we can get a constant number of rounds in expectation. And this is because, for example, for the equal revenue, the expected value of the max of n draws from the equal revenue distribution is n. And so we just need to run rounds until we reach n, and then we're more likely to stall. And by setting epsilon equal to n, one round suffices to reach the expected value of the max of n bids, because we just jump to the expected revenue, and after that, there's not much left to do. Note that the problem is that if you really want constant expected rounds, you need a very high epsilon to cover a lot in just one round. And so this step size is not very ideal, and an interesting thing to do would be to play around with it. So to recap, our main result is that ADRA is credible, meaning that the seller is honest. It is truthful, meaning that the bidders bid their true value. It is revenue optimal, meaning that it maximizes the revenue. It terminates in constant rounds in expectation, meaning that the maximal number of times that the seller needs to communicate with any of the bidders is constant in expectation. And it works for all distributions, meaning that it works for regular and irregular distributions. And other side results that we had was that for ADRA, we can get exponential improvement over the ascending price auction, and we can always get an instance of ADRA that has constant communication complexity. So to conclude, we identified a new single item auction that is credible, truthful, optimal, terminates in constant rounds in expectation, and that works for all distributions. And potential next steps would be to see if we are able to reduce the required deposits. That would be an interesting open question that has practical implications. Although it's important to note that ADRA requires no bidder to deposit more than 1 plus epsilon fraction of their value. Another direction that would be interesting is to extend the credibility of ADRA beyond the IID framework. So for example, if we had values drawn independently, but from different distributions. And that's it. Thank you.